Hi everyone and welcome back to your channel Fundamentals of Engineering with Farhad. Mechanics of Materials, maximum deflection calculation in a fixed support beam with a distributed load of W. Solution 1. In the first solution, we'll solve this 1-degree indeterminate beam, which is a fixed support beam with a distributed load of W on top of it with the help of the integration of moment equation or elastic curve integration. So if this is A and B, we have like evenly distributed reactions for R sub A and R sub B due to the symmetry, and that's WL over 2. There are two identical moment MA and MB developed at the fixed support and also delta maximum, which we are looking for in this problem. So in the first solution, which is the determination of elastic curve from the moment equation, we can consider it like this is our first solution, elastic curve from moment. And in solution 2, in next video, we'll solve it with the moment area approach. So if we cut our beam through with the length of x from each of these support like A, then develop the moment equation for that length. So the resultant of Wx applies at the center of that length, which is x over 2 from each side. Then Ra, which is half of the load on the original beam, which is WL over 2, and definitely we have like two moment M sub x at the length of x and M sub A in the original beam. Then summation of moment in x direction for our arbitrary direction is counterclockwise positive, including the mx itself goes 0, so it just gives us a mx plus wx squared over 2 minus wl x over 2 plus ma equal to 0. So this is our mx, which is a positive, a plus a wx times x over 2 this moment minus the moment created or developed from the Ra, which is a clockwise, that's a negative, plus Ma, which is again counterclockwise, that's a positive moment. As soon as we have our moment equation, then we can jot it down, and by integrated once, so d squared y over dx squared is equal to 1 over ei times the moment equation. So if we integrate it once, we get the theta equation, and constant c1 create into the first integration, and if we integrate it twice, it just gives us the delta equation, and also the second constant develops. Now by applying the boundary condition for our theta and delta equation, and which is our equations, and also the condition on the beam, so at x equal to 0 we don't have a angle of rotation, and we don't have like any side sway, up and flip-flop, which is any up and downward motion, because it's fixed. Likewise at x equal to L we have the same condition, no theta, no delta. And if we call these condition like A, B, C, D, our theta equation is equation 1, our delta is called equation 2, and then these are our boundary condition. And by applying equation 1, theta equation, and A, it just simply says C1 is equal to 0, and applying equation 2, delta equation, and this time like B, it just gives us C2 is equal to 0, and by applying equation 1 and C, it just simply gives us the MA is equal to a WL squared over 2. As soon as we have MA is identical to MB due to the symmetry of our condition, our geometry. So if we just simply intuitively, we can easily see the delta maximum occurs at the center. So y maximum at x is equal to L over 2. Replace x equal to L over 2 in the equation of delta, it just simply gives us y maximum is equal to a downward WL to the force over 384 EI. That's our delta maximum for a fixed support beam with a distributed load of W on top of it. And if you make a comparison with for of a fixed support beam with similar loading but on a too simple support beam, you can easily see for a too simple supported beam, delta maximum is increased by 5 times. And that makes sense because in the fixed support, the fixed support prevents from the creating any angle and also restrict the downward motion. That's why the delta maximum for a fixed is like 1/5 of the delta maximum for a too simple supported beam. Thank you. We'll solve the same problem with an easier approach for a next video, which is a moment area method. Thank you.